Now let's create an action client node for the Fibonacci action we created in the last video. We don't need any new dependencies, so we're going to jump right into the C++ code. Our node will look similar to the server because it's an asynchronous callback-based structure, but we're now working on the other end of the interaction, the client, instead of the server. We'll again start by defining some convenience type aliases, the same Fibonacci type for the type of the action, and then a goal handle type, this time using a client goal handle for the Fibonacci action type. We'll have a private member for the client called client, and then we're also going to need a timer for this example, so we'll create one of those called timer. In our constructor, we initialize the client with RCL-CPP action create client, which just needs the type of the action, a handle to the node from the this pointer, and the name of the action to call. Then we'll initialize our timer, like normal, giving it the callback timer callback. Now this timer is actually what's known as a single shot timer. It's a timer that will wait for the duration and trigger the callback exactly once. We're using this single shot timer so that we play nicely with the ROS event system. We want to make sure that our client sends the goal after our node has been fully constructed and our ROS event loop is started. The thing that makes this a single shot timer instead of a normal one that will repeat forever is that the first line in our timer callback function calls timer cancel. So our timer will wait the 1 second defined in its duration, call timer callback, and then immediately get canceled. So no further calls to timer callback will happen. Inside of our timer callback, the main thing that we're doing is constructing a goal, setting its order to 4, and sending it with the function async send goal. This section here that initializes this goal options object just defines different callbacks that we'll be interested in for the different status updates we get associated with this goal. The first callback is the goal response callback that lets us know if the server accepted or rejected our goal. The second callback is the feedback callback. That gets called every time there's a new feedback message available from the server. And finally, we have the result callback. That gets called when the final result for our goal is available from the action server. We bind all of these callback functions in the goal options object and then pass that in along with the goal to the async send goal function. So far all we've done is create a single shot timer that will wait for 1 second and then fire a callback and immediately get canceled. Within that callback, we construct our goal and send it to the action server. Everything else will happen in those callbacks that we gave to the async send goal function. And because this is a simple demo node, all those callbacks will just print out the information that we get in the callback parameters. Starting with the goal response callback, we get in as a parameter a future to a goal handle. So our first step is to wait for that future to be ready and get the goal handle from it. And then we check if the goal handle is a null pointer or not. If it's a null pointer, we know that the server rejected our goal and we can log that out. If it's not, then we know that the server accepted our goal and we actually have a valid goal handle. And in this case, we'll again just log that information. Because action servers can run with multiple goals at the same time, we need some way of identifying each goal. So each goal gets a universally unique identifier associated with it. In our goal response callback, we can get that ID from our goal handle with the getGoalID function. Then there's a helper RCL-CPP action to string that converts that into a human-readable string of numbers. Most of the time, we can ignore this ID because a lot of action servers really only run one action at a time. But if you do get into a situation where you have one server juggling multiple goals at the same time, keeping track of the identifiers becomes more important. The next callback is our feedback callback. This again takes a goal handle pointer and a feedback message. And because this is again just a simple demo node, we're just printing out the goal ID and the size of the sequence in our feedback message. Finally, we have a result callback. This callback takes in a wrapped result. This is the result message from our action definition wrapped with some metadata about the status of the goal and its ID. The structure of a result callback here is based around a switch statement on the status code in our wrapped result. This code tells us whether the goal succeeded, was canceled, or aborted. So we have a case for each of those states. In the first, if we succeed, we log the ID and the final number in our Fibonacci sequence. If our goal was aborted, we log that along with its ID. And similarly, if it was canceled, we'll log that that goal ID was canceled. It is possible for us to lose connection to the action server altogether and get an unknown response code back, so we have a default case that just lets our user know that we don't know what happened to this goal. Finally, because this is a demo node that just triggers the action once and then should clean itself up, the end of our result callback actually calls RCL CPP shutdown, which will kill this node. And now you can see the general flow of an action client. We start using async send goal to send our goal to the server. We then get back whether the server accepted or rejected that goal. If it was accepted, it will start executing and we'll get feedback messages. And finally, when the goal reaches a terminal state, we'll get a callback to our result callback, and we can check that state and the result associated with it. With our workspace built, we can now open two terminals to demonstrate our new client. In the first, we'll run the action server node we wrote in the last video. And in the second, we'll run our new client node. In the log output, we can see that our client sent a goal, which was accepted by the server, and then received a number of feedback messages as the sequence grew, and then received a final result with the goal succeeding and giving us the Fibonacci number of 3. And that's all for actions. They're a useful interface for managing long-running tasks in ROS. They show up frequently in things like the nav2 navigation stack and are a great way to trigger your robot's overall behavior.